So I'm Khaled Kabi. I'm a second-year graduate student at Dinca's lab. My project is concerned with the design of electrochromic metal organic frameworks for smart Windows applications. Let me start with the definition of metal organic frameworks. They're a class of crystalline, porous materials, usually designed by the combination of organic linkers with metal nodes or metal clusters. The main features of these materials is their high porosity as well as their compositional and structural tunability. The structural and compositional tunability comes from the ability to combine a variety of different organic linkers with different metal centers and metal nodes. And the porosity comes from the topology of the materials and the framework that comes out of making these materials. These materials are very porous. They can reach surface areas that are equivalent to an entire football field per gram of material. And because of that, they've been investigated for a variety of different applications, including gas storage, catalysis, and other applications too, such as electrochromism. Electrochromism or electrochromic materials are defined as those that exhibit reversible color switching between two or more states by the application of electric potential. And usually the origin of this color change is redox behavior or electron transfer behavior within the material. These materials are especially important for energy-saving applications, such as smart windows and energy-saving buildings and in displays, also in light-dimming mirrors in cars, for example. Usually the beneficial preferred color switching is between a transparent state and a colored state. And for these applications, a wide variety of materials have been investigated, including transition metal oxides, organic-based materials, and hybrid materials, organic and inorganic hybrid materials. And each of these materials has its own advantages and disadvantages. And because of that, people have come up with metrics to evaluate the performance of these materials. And these metrics include switching time, which is a measure of the speed of the system, how fast the system is switching from one state to the other. And coloration efficiency, which is the intensity of color that you get per charge you inject into the system. There's the write erase efficiency, which is a measure of the memory of the system, how much of the color state remains after you switch back to the transparent state, and the long-term stability of the material. For example, transition metal oxides, which are commercially used in smart windows, have slow switching times, low coloration efficiencies, but they have excellent stability, excellent write erase efficiency, and they're cost effective. On the other hand, organic-based materials and hybrid materials have usually intense colors and fast switching times, but they suffer in terms of stability and cost. And this is where we think metal organic frameworks could improve some of these metrics because of the high porosity in these materials and the tunable structures. The high porosity would facilitate ion transport within the material, allowing for fast switching times. And the tunable structures would allow for the design of materials that exhibit excellent coloration efficiencies and excellent stability. And this is what we want to do. So in order to design an electrochromic metal organic framework, we incorporated a class of molecules known as naphthalene diimides. These molecules have interesting optical and electronic properties, and we wanted to incorporate them in a structure that's very porous to facilitate ion transport within the material. So we designed this MOF, which we name as MNDISA. It's very porous. It has a pore size of about 33 angstroms, which is a mesoporous material, meaning it's very highly porous. And we expect that it's going to allow for fast ion transport within the material. Usually, these materials are obtained as powders, so making thin films of them for electrochromic applications is a bit challenging. So I had to do a little bit more work in that area. And by tweaking the solvent systems we use, we managed to obtain thin films of these materials, as you can see on the right. These films are deposited on fluorine-doped tin oxide electrode. And we can characterize them by powder X-ray diffraction and UV vis. And they show very nice optical response, and they're smooth films. And in order to characterize them, oh, too bad. I used to have SEM images of my films, so I'm just going to skip that. The films are very dense. Oh, here they are. The films are very dense and very uniform on the surface, which is good because it's going to result in an intense color response when we switch from one state to the other. And in order to evaluate the electrochromic response to these materials, we had to investigate their electrochemistry and spectroelectrochemistry. And we see that the material exhibits reversible behavior between reduced and oxidized states, which is what we wanted. We can cycle it up to, actually, I tried up to 10 cycles. I'm showing 6 cycles over here without any loss of the stability of the material or the crystallinity of the material, which is good in terms of applications. And if you can see on the right, when I was doing the electrochemistry, you can see a switching from the transparent state to a very dark state. Hopefully it's clear over there. And that dark state is almost black, which is beneficial for smart Windows applications. It was the kind of response we were hoping for. And in order to investigate the origin of this color change and the reversibility of the color change, we performed spectroelectrochemistry. And we see that the color can be switched from transparent to almost black by the application of potential window of 1 to 1.5 volts. And we can go back to the neutral state by applying the reverse potential. The switching time of this system is about 7 seconds to obtain the radical anion, and additional 23 seconds to obtain the dianion, which is the second reduction of the system. And this switching is reversible, as I mentioned. And this switching time is actually fast, but can be improved by changing the thickness of the film as well as the electrolyte of choice. And we hope with this result we can actually incorporate these materials in an actual device for commercial applications. With that, I would like to thank my group, Professor Mirsha Dinca for his support, and the rest of the Dinca group, as well as the Deshpande and Master centers for their funding. Thank you.